Hello everybody, this is Mr. McAllen, and today I'm going to be talking about what a linearization is and how to use it to approximate a value of a function. Now, first thing is we should remember that when a linearization is simply an extension of an equation of a tangent line. Remember what you need for an equation of a tangent line. You need a function, you need a point, a slope, and the derivative. So here we go. We're going to write an equation of a tangent line to our function is going to be the square root of 1 plus x. Now this is just a sketch of it, or as it says down below, 1 plus x is our function. And we're going to come up with, just as a sketch, showing what the equation of tangency would be, or the line of tangency would be at x equals 0. So we're going to call our linearization eventually L of x. And that's just a formal way of writing down, as you can see here, y. We're going to just rename that L of x. And that's all it is. It's basically just reforming this equation so that L of x is equal to, we'll call this y1, but that's really, that's just the y coordinate plus the slope times x minus x1. So what we need to do for this is, if we're going to be doing it with this function, we need to figure out what our center point of the approximation is, x equals 0. We need to find f of 0, because that would be what y1 would be equal to. And we need to find f prime at 0. That will be the equivalent of our slope. So let's do that. Remember what the derivative of a square root function is. The derivative is 1 over 2 root 1 plus x. There's no need for the chain rule because the chain rule derivative would be 1. So f at 0 is equal to 1/2 when we plug, f prime at 0 is equal to 1/2 when we plug 0 in for x. F at 0 is equal to it's equal to just the square root of 1 plus 0, which is square root of 1, which is 1. And our x value is 0. So when we write out our equation of a tangent line, we have y minus 1 equals, just writing out the equation for you, we have 1/2 times x minus 0. So this would be adequate for the AP calculus test to write out your equation with line in point and slope form. But if we were writing it in terms of a linearization and calling it L of x, we would want to shift that 1 to the other side. So we would have 1 plus 1/2 of x. And this would be our formal linearization of the function. Let's take a look and see how close this approximation is to the actual curve. And what I'm using is this internet tool called Desmos. And as you look on the graph here at the right, I'm just going to zoom out so you can see the square root function has been moved over. Let's just look at the square root function. There you can see the function is all, it has its basic shape. And the linearization I programmed in is 1 plus 1/2 x. And you can see that from a distance, it looks good, really in a local sense to the graph. But as you get closer and closer, you can see how the line and the curve actually, they aren't the same except at the point of tangency, but they're really close. How close? Well, on the table here, I would look at, since the center of approximation is at 0, let's look at 0.1. I put in the wrong point. Let me put in 0.1. And you can see that the function and the linearization are within 0.2% or closer. I'm just estimating that off the top of my head. Hopefully I'm not making too bad of an estimation. And here we have let me click on the right values at 0.02. You can see at 0.02, it's the actual value is 1.00995, and the approximate value is 1.00995. 1. And if you look at the points here on the graph, they look almost indistinguishable with each other, as far as where we're at exactly. So I'm going to turn that point on, and you can see the green dot is on top of the green dot. They are really, really close. I would almost consider them to be the same. So what we're trying to show, or what I'm trying to show with this, is that the linearization is a really, really good approximation as long as you are very, very close to the center point of the approximation. I just did a screen capture here, so I'm going to bring that back into the software so that we can, maybe just talk about that a little bit more. Again, the idea here, the calculus idea, the curricular idea is that when you're looking at a linearization, the function, because the center point of the approximation is at 0, if you go far away from your center point of the approximation, let's say your x equals 1, you could see here that there's a definite error between the two. There's error between the two no matter what, but the error becomes more pronounced the further away from the approximation you get. And if you go to the left, the same amount, you could see that the error also is getting larger and larger as you walk away from the center of approximation. Well, I hope this video has helped you understand what a linearization is used for, because it's definitely easier to compute a linear function in terms of if somebody asks you to guess what the square root of 1.01, you would be far better off to use this approximation, the linearization, to make your guess than to try to figure out the square root of 1.01. So hopefully I've made that point, and look for the next video where what we're going to do is we're going to work on writing out a linearization formula for a more advanced function, and we're going to actually analyze the error if we walk away from that approximation.